All right, so let's start with the fundamental theorem of calculus. And we are taking questions from definite integral. So if you look at the definite integral, you have integration from a to b f of x dx. So we can say that this is the function f of x and the ordinates for x equals a, x equals b coming from x-axis. And you make two vertical lines. So this is the region bounded by this boundaries and the function. So the definite integral, you have a to b f of x dx basically gives you the area of this region here. Okay, so what happens when you see some integral like this? So this one is the function here, 2x minus 2. If you draw, it will be straight line. And that picture I have mentioned in here. So we'll see this solution in two ways. One is as a fundamental theorem. So what we see here, that you take the integral of this function and you get a new function. And that function is actually here, which is 2 times integral of x will be x squared over 2 minus 2 is a constant, and then integral is to x. Now the bounds we have negative 2 to 4. So first we'll replace x by 4, we get some result, and then you subtract when you replace x by negative 2. So that exactly right here. So first you replace x by 4, 4 is squared minus 2 times 4, this is one part. Now we have a minus here. Then again we replace this x by negative 2, square it, minus 2 times x is replaced by negative 2. And further you simplify, you get 16 minus 8 is the first part from the upper boundary. And here we have negative 2 squared will make it 4, as you know. Then minus 2 times negative 2 gives you another positive 4. At the end, when you simplify, you get 0. So let's look at the graph, why it is 0. So when we plot the function 2x minus 2, this is the straight line goes like this. And as you know, the slope is 2 and the y-intercept is negative 2. That you can see exactly here. You can just the graphing calculator and check this. Just let me see here. I'm writing my function, which is 2x minus 2. 2x minus 2. And graph it. So this is the line. Go here. And we are taking x is negative 2 here and positive 2 here. So we get two triangles. The area of this triangle here will be 1/2 times base times height. So base is 3, height is 4. And since it is below the x-axis, we put a negative in front. So that's why we get negative 6. The other side triangle here, base is 3, height is 4. So again, 1/2 times 3 times 4, that is 6. When you add these two triangles together, the area gives you 0. That exactly we have found here too. The second example now, we have semicircle of radius 3. And as you see in the shaded region, we are just taking 1/2 of the area of a circle. And everybody knows the area of a circle will be pi radius squared. In this case, radius is 3, so we are writing pi 3 squared. And since we are taking half of the circle, we multiply by half. So the answer is 9/2 pi from the graph. The next example, this region is given actually, no function given to you. This is the region given. Now, if you look at here, you have one triangle below the x-axis, so that area will be negative. So we are writing 1/2 and with a negative sign times base is this length, the length we are talking about. So it's 2 units, and this is 1 unit. Okay, so that's the area for this triangle. The other side, you call it a trapezoid. Of course, you could make a line from here so that you get a triangle and a rectangle. You don't have to do that way. You can just use the concept of finding area of a trapezoid. We know which is 1/2 times height. So height is actually this one. And then sum of the parallel sides. If you start from 0 to 6, which is 6 units, and that one is mentioned here is 4. So altogether, after simplification, we got 9. Okay. Next. Now we are taking one example here, the practical example. A train is moving at a velocity of 76 meters per second when it hits the brakes. It slows down at a constant rate of 0.8 meters per second each second until it stops. After it hits its brakes, how many meters will it move before it stops? That's the whole question. So first of all, we see that we have initial velocity is 76. That means when the time is 0, velocity is 76. That we'll write down here. And the rate is 0.8, slowing down. So that's why it's the dv dt, which is the derivative of the velocity, is 0.8. So this is our function actually. From here, we will collect velocity with the help of integration. So first of all, you multiply both sides by dt. You get dv equals 0.8 dt. Now, when you take the integral both sides, you get v equals, I just dropped this line, you can easily understand that integration dv will be just v, and this one is negative 0.8. This is 1 here, that's why t, just like here, you have 1 here. With respect to v, this gives you v, that one will give you t plus integral constant. And this is the velocity function at time t. If you replace t by 0, then you see that v0 is this one, 0.8 times 0 is 0. So you got c equals 76. So this is my velocity function. And also we know by definition that the velocity is the rate of change of displacement. So that's why we can write next vt is s prime t. But here we want to see what was the time when the velocity is 0. So when you write velocity is 0, so you get 0 equals 0.8 t plus 76. So t will be 76 over 0.8. You can use calculator and find the answer. Next part is s prime t is that one which was the velocity, is the rate of change of displacement. So s prime t is ds dt, and we follow the same process. And the question asks you that what was the displacement when it stops? And we have found the time to stop is 95. So then you take the integral from 0 to 95, and that's the function here. And this part, I hope you can easily understand. So then 0.8, negative 0.8, leave it there. T will be t squared over 2 and 70, 60. And as before, you just plug 95 for t for this, and then here also. And after that also you can plug 0. 0 will give it whole thing 0. So take a piece of paper and simplify this answer. You'll find it 3,610 meters.